In Part 2 of Lecture 2, we will look at a brief introduction to formal language theory. Before we talk about how scanning is done, we need to take a look at a brief introduction to formal language theory, and that starts us off with a few definitions. A string is a sequence of symbols, but symbols can mean different things depending on what exactly we're doing. In the example you see as symbols the capital letters A and B, the lowercase ABB, the uppercase C, lowercase a, and uppercase C. These individual letters are symbols. In the example below, the lexemes that we have and the tokens to which they correspond are symbols in their own right. An alphabet assumes that we have a finite set of symbols. If we're working with the Latin alphabet, our ABCs, that will literally be the letters A through Z. Or it could be the 10 digits we work with, 0 through 9. But if we're taking a look at a programming language, as you can see here an example from Pascal, our alphabet can be the reserved words that you see here. A language is any set of strings over an alphabet. That set of strings may be finite in some cases, but usually is infinite. And we'll take a look at that very soon. A graph is a finite set of vertices and arcs, as you can see in this diagram. I have 4 nodes, A, B, C, and D, and a variety of arrows that take you from one to the other. A tree is a directed graph without circuits. Directed means that there is a difference between going from A to B, and if it's allowed, going from B to A. The lack of a circuit is something that you'll see here. I can go from A to B to E, but there is no path that takes me back to A. Similarly, there is no path I can travel that will take me from any node all the way back to itself. The tree that you see here is a binary tree. In every instance, each node that has children has 2. It could even have a few with only 1 child, as long as I never have more than 2 children for a given node. If I have a situation where there can be, and frequently will be, more than 2 children, that would constitute a general tree. 2 terms that we will need to get familiar with are terminals and non-terminals. A terminal is a symbol within the alphabet of a given language. In formal language theory, we represent them by lowercase Latin letters, such as little a and little b, as you see here. If I am parsing, in that case, my terminals are the tokens of the language. For example, int, while, and class, all of which are terminals in the C++ language. Non-terminals are combinations of terminals. A combination of terminals can be derived from a non-terminal if we follow the rules or the productions of the grammar of a language. Typically, these will be represented by capital Latin letters, as you see here, for example, capital A and capital B. What you see here are examples of non-terminals and productions in which they may appear. The grammar that you see here is for basic expressions. An expression will be comprised of a term, followed by 0 or more occurrences of a plus or minus sign, followed by another term. A term is comprised of a factor, and then 0 or more occurrences of either an asterisk for multiplication or a slash for division, and an additional factor. Factors can either be an identifier or a constant. Variables, which can be either a terminal or non-terminal, are usually represented by a Greek letter. For example, in this case, beta. The Chomsky hierarchy was first proposed by Noam Chomsky in 1956. It says that there are 3 different types of languages and the theoretical machines that can be used to process them. Type 0 is recursively enumerable or unrestricted, and it takes the theoretical Turing machine to process this. Type 1 is context-sensitive languages, very much like human spoken languages. These can be processed by a linear bounded Turing machine, which differs from a Turing machine by the fact that it is finite in size. Type 2 is context-free, something that we will see with the syntax of programming languages. These can be processed by push-down automata. The most restrictive language are regular expressions, which can be processed by a finite automaton, which is a fairly simple machine that does not make any transformations, but can either accept or reject strings that we produce from it. Type 0, recursive, enumerable, or unrestricted, can be represented by alpha derives beta, where alpha and beta both can be any string or any variable. Type 1, context-sensitive, takes the form of alpha derives beta, where the length of alpha is less than the length of beta, and at least one of alpha's characters is a non-terminal. Type 2, or context-free, is represented by A derives beta, where there is one and only one non-terminal on the left-hand side, and no terminals at all on the left. Type 3 is regular, which is represented by A derives little a, or capital A derives little a followed by little b. Most programming languages are almost all context-free, although there are a few context-sensitive traits that may show up in specific languages. A Turing machine is the theoretical machine that Alan Turing proposed. Given a particular input stream, it performs as many computations as necessary, finally deciding whether to accept if the string is in the language or not. A linear bounded automaton works just like a Turing machine, but limits the space to the length of the input string. In both cases, it works with a model of tape going back and forth over a recording head. A push-down automaton is a collection of states and a stack. It uses the stack, and the only thing it reads is what is on the stack. A finite automaton does not write anything at all. It is a collection of states, and as it reads a string, it will move from one state to another. If it ends up in a final state, it accepts the string. Otherwise, it rejects it. In theory, computers can be as powerful as Turing machines, capable of doing a very large number of different types of processes.